Good morning, dear students. Next topic, what we have from module 3 is Poissons and Laplace equation. Let's understand what is a Poissons equation. In a static electric field, curl of electric field intensity, that is del cross E, we call it as, which is equal to minus dB by dt. This is magnetic field intensity B we have. So this is equal to 0. This is what we have equation where E, that is electric field intensity, E is equal to the gradient of V, that is voltage we have. So if there is a moment of charge happening in an electric field, then we can define potential difference of the 2 points wherein which movement of electric charge happen, and because of that potential difference, you can define what is the electric field intensity, or we call it as electric field intensity is equal to the gradient minus gradient of V, we call it as, where V is the potential difference. So we have this equation and we know that the curl of E is equal to 0. Curl of E represent the rotation of E. We know that electric field will not rotate. Electric field, you will not see it is rotating. You can see that it is expanding or contracting, whereas the rotation you will not find. So static electric field cannot rotate. So the curl of that E is always 0, and electric field we can also express as the gradient of V here, as a function of gradient of V here. So this is what the equation we have, E is equal to minus del V. With these two equations, we are trying to understand what is Poisson's equation here. So we know that the divergent of electric field intensity, electric flux density, we call it as electric flux density D, that is divergent of that is del dot. This you please understand it as a dot operator, del dot D, that is divergent of electric field intensity, V is equal to rho. This is what we have, a point form of Gauss law. We call it as, this is a point form of a Gauss law. We can write like this: divergent of D is equal to rho, where rho is the charge distribution. So our charge density we call it as. Now D we can express in terms of E. How can we represent? We know that D is equal to, that is flux density, electric flux density D is equal to epsilon times the electric field intensity. So if I replace this D with E, then I can write it as epsilon E, where E I'll be replacing with minus del V. So I'll be replacing here minus del V, but that minus I'm sending to the right. So I can write divergent of D is equal to rho. This equation, that is from Gauss law, we got this equation. This is a point form of a Gauss law, we call it as. So it is del dot D is equal to rho, where D we are replacing with the E, in turn E is replaced with gradient of V. So we found that del dot epsilon gradient of V is equal to minus rho. Now we assume that here epsilon is uniform, that is wherein which we are applying Poisson's law. We found that the permittivity is not changing. That means a uniform medium we have. Then we can write this as epsilon into del operator dot gradient of V is equal to minus rho. Since this epsilon is not changing, it's uniform, I can take that to the right hand side. It is not getting affected by a dot operator. So we are just taking that to the right side. It will come here in the denominator. So I'll be having an equation del dot del V is equal to minus rho by epsilon. So del square V is equal to minus rho by epsilon is what we have a Poisson's equation. So we started with, for a static electric field, we found that the curl of electric field is 0, and electric field is represented as the gradient of V here, gradient of potential difference. And then we have a divergent of D is equal to rho according to Gauss law. We have, and D we are replacing with E. In turn, E is replaced with divergent of V. So we have an equation here, del dot epsilon del V here, which is equal to minus rho. Since epsilon here is uniform, considering medium to be same here throughout, so we can write an equation like this, taking epsilon to the right, we got it here in the denominator. So we have del square V is equal to minus rho by epsilon. This is what we have a Poisson's equation. This is what we call it as Poisson's equation. You can expand that. What is del square? That is second degree del operator we have here. This is also called as Laplacian. So this is what we have a representation of del square V here. And if you are considering only one dimension, then it will be del square V by del x square. So this is what we have, one dimension representation of Poisson's equation. Otherwise, a 3D equation, three-dimensional equation in a Cartesian form, we will be having something like this. This is what we call it as a Poisson's equation. Next, we have Laplace equation. Laplace equation, we will get it from Poisson's equation by substituting rho is equal to 0. What does it mean? We are going to assume that in a closed surface, there is no charge. If there is no charge enclosed by the closed surface, then rho will be 0 or the charge will be 0. That is what we call it as a Laplace equation. So we equate rho is equal to 0 in a Poisson's equation. If you are equating rho 0, then you will be getting del square V is equal to 0. And this is what we call it as a Laplace equation. What is a Laplace equation? I repeat, it is same as Poisson's equation, only a condition we are going to apply, that is the closed surface doesn't have any charge, that means rho becomes 0, then you will be having a Laplace equation, and Laplace equation says that del square V is equal to 0. Why? Because rho is becoming 0. So the Poisson's equation will become Laplace equation if you substitute rho is equal to 0. As epsilon changes, that is, if it is a non-uniform epsilon, you will be having a different situation. That's what given here in this equation. For a uniform, let us understand uniform epsilon, we will find that del square V is equal to 0 as the Laplace equation. Now, okay. Now let us take a parallel plate capacitor. Let us try to find solution to Laplace equation. So del square V is equal to 0 is what the Laplace equation you have. You can find the solution. Finding solution to this second order differential equation is finding a value of V. So we have to talk about one more theorem that we will take up in the next video. That is uniqueness theorem, we call it as. What is that uniqueness theorem says? This Laplace equation is a second order differential equation. We will be expecting two solutions. But here in this situation, we found that only one potential difference we satisfy this condition of del square V becoming 0. So we will see that it's only one solution exists here. So we will be having one unique value here. For that, this Laplace condition will be satisfied. So del square V is equal to 0, and you can find a solution to this equation, that is finding a value for V. And surprisingly, we found that this V will be unique. Instead of getting two values, we'll be getting only one value here. That is what we call it as solution to this Laplace equation. So let us consider here a parallel plate capacitor here. I have a parallel plate capacitor, X is equal to 0. I can call this as a cathode, where V is equal to 0. And this is what I call it as anode, which is having a distance D here. That is, D is the distance between the two plates of capacitor. I have X is equal to 0 here, X is equal to D I have here. This is having a voltage 0, potential 0, and this is having a potential V naught here. If this is the situation, neglecting the fringing of field at the edges, we found that at the edges you will see that it is reducing, but still we can ignore that and we can say that V is equal to V of X. So del square V is equal to del square V by del X square is equal to 0. This is according to the Laplace equation. So we can write that del V is equal to del X, because If a second degree derivative of a variable is 0, then first derivative should be a constant. First derivative should, first derivative should be a constant. So we will be having an equation here that is first degree, we will be having first derivative is having a, then v can be equal to a into x plus b, where is, with respect to s we will be differentiating. So a into x plus b is what the solution, we call it as a general solution to this Laplace equation. So once we have arrived at this, we will be referring this condition, that is x will be d, then v is equal to v naught, and x, if x is 0, v will be 0. We will apply this condition to find out the constants what we have here, constant a and b what we have here in the general solution of this v. So let's do that. So we know that v is equal to 0 at x is equal to 0, and we know that potential at the other plate is v naught, and this is having a distance x. So now substituting these two conditions, I can find out a and b constant. So what I do is, I'll take this equation, and if for this equation, I'll be substitute x is equal to 0. If x is equal to 0, v is equal to 0. So 0 is equal to 0 plus b I'll be getting. So I can say that b is equal to 0. So that's what we have taken here, b is equal to 0. Now, take any one equation and we can substitute b 0. Then if I take an equation, b naught is equal to into a into d plus 0 we have, because we know that x is equal to d in the second case. So I'll be substituting x is equal to d here. Then a is equal to v naught divided by d we have. So we'll be getting a value a. Very simple here. What you have to do is you have to construct two equations. So one equation based on this condition, the another one equation based on this condition. You get two equations. So first equation we found that it's becoming 0. In the second equation, I'll be applying this condition. So v naught is equal to v is equal to v naught at x is equal to d, and we know that b is equal to 0 already. So I'll be getting now a is equal to v naught by d. So now v is equal to v naught by d into x. This is what we call it as a particular solution. Now, once we know what is v here, once we know the value of v, which is v naught divided by d into x, what I do is I can get an expression for electric field intensity. Electric field intensity, according to equation which we have already learned while deriving a Poisson's equation, it says that minus gradient v, and gradient is what we have del v by del x. So this is what we have, minus del v by del x into ax, where v is equal to v naught by d into x. If I substitute v is equal to v naught divided by d into x, then I'll be getting electric field intensity E is equal to minus v naught divided by d into ax. This is what we have an value for electric field intensity. So we constructed a Poisson Laplace equation, and through that we could get a value for electric field intensity. Thank you.